Chapter 1, Lesson 1. We're going to be talking about chemistry, matter, and measurements. First off, what is matter? Matter is anything that takes up space and has a mass. So if you think about it, matter is pretty much everything around us. So even the air around us, right? The air around us, it has a mass, even though the mass is very, very small, and it takes up space. You yourself are made of matter. Anything that you touch, look at, see is also made of matter. So what is chemistry then? Well, chemistry is the study of matter and the changes that it undergoes. So if you think about that, chemistry is really the study of everything around us and the changes that everything around us can undergo. So it's really a very, very wide topic. The daily learning goal for today is we're going to learn about physical and chemical changes of matter. We're also going to learn how to describe and tell the difference between pure substances and mixtures, and this will lead us into an introduction to separation strategies. So review for this lesson, this is the vocabulary terms that we're going to learn. So we'll learn about chemistry, obviously, an atom, a definition of an element and a compound and the difference between the two. Also the definition of physical and chemical properties and changes and their differences and how to tell. Also homogeneous mixtures and heterogeneous mixtures. First, we're going to look at physical properties. So physical properties can be separated into two categories, qualitative and quantitative. So for qualitative physical properties, the amount of the substance does not matter. So qualitative properties generally have to do with appearance or with things that can't be measured. So since the amount doesn't matter, its qualitative properties are generally things that can't be measured, such as smell, taste, sound, color, right? You can see the color of something like a pencil. If I ask you the color of the pencil in front of you, you can tell me what the color of the pencil is, and it doesn't matter how big the pencil is. It doesn't matter the amount of pencil that is there. Same with if we are talking about the color of a reaction once we get into lab, right? The amount of the substance that you're looking at doesn't matter in order for you to figure out what the color is. Same goes with smell, texture, the texture of something, the amount doesn't matter. You could have a small piece or a large piece. The texture will be the same. Now for quantitative then, you can see quantitative does depend on the amount of a substance. So some examples of quantitative physical properties would be mass, because mass would depend upon the amount of a substance, right? If you had a very large pile of sodium chloride salt or a very small pile of sodium chloride salt, right? The small pile would have a smaller mass than the large pile. So mass is dependent upon the amount. Length also dependent upon the amount. Do you have a very tiny nubby pencil or do you have a very large new pencil? Volume, time, voltage, force, density, those are also examples of quantitative physical properties. States of matter is also a physical property. So when I'm talking about states of matter, what we're mainly focusing on is solid, liquid, and gas, because those are the states of matter that you have probably seen most often. Right? A solid melts, forming a liquid, then the liquid can be heated up further until it evaporates and forms a gas. Now there are also two other types of matter, being plasma and the Bose-Einstein condensate. We won't be focusing on those, but I just want you to know that they do indeed exist. Physical changes. What are physical changes? Physical changes are when the morphology of a substance is being altered. So what exactly is morphology? Morphology of a substance is just a big word for any change in size, shape, or physical state. So as we saw on the previous slide, states of matter are physical properties. So when the state of matter changes, that would be a physical change. And that's what we are seeing in this first example. The states of matter are being changed. So what do I mean by that? Well, in this example, we have a solid river with a melted portion in the middle, so a frozen river. Now, this is a change in the states of matter, which is a physical property, therefore a physical change, because we have solid lake and liquid lake. So if we go from a solid to a liquid, that is then a physical change. Let's look at the second example. So the second example, it looks like we have a copper pot, and the copper pot is being heated. You can tell by this bright redness of the pot itself. So since the pot is being heated, what we have then is a temperature change. And since temperature is a physical property, something changing in temperature is going to be a physical change. So pot being heated, physical change. Now let's look at the last example. This one's a little bit harder to see, in my opinion. So in here we have a spring. Now the spring can be pulled apart. So you can grab both ends of the spring and pull it to make it longer. So what we're doing then is we're changing the size, we're changing the length of the spring. And we're probably also changing the shape a little bit, because when we stretch it out, the shape is going to slightly change because the spring itself is going to become a little more stretched. So this is also a physical change. Keep in mind that physical changes, there is no change in the identity of the substance. So what I mean by that is, in that first example, that lake is still made up of water. Even though it went from a solid to a liquid, it's still the same substance. It's still water. Same with the pot. The pot is still made of copper no matter the temperature. So the identity of the substance does not change, just the size, the shape, or the physical state. So now that we've talked about physical properties, let's look at chemical properties. So what exactly is a chemical property? Well, a chemical property is going to be a change in the chemical makeup. So this is where the substance is actually changing and forming a new substance. We often see this with reactions, so with the way a substance can change or react to form other substances. The most common one that we see, the most common chemical property that we're going to see, is flammability. So I'm just going to circle that one here. You can see it pictured as one of the chemical properties, and we'll see it on some of the lab bottles as well. So in order to test the flammability of a substance, we would have to do what? Start it on fire. So if we started it on fire, it is no longer going to be that substance once we're done, right? Because when we start it on fire, we are changing it into ash. So it is changing from, say you're starting cardboard on fire. Once you're done starting it on fire, it's no longer cardboard. It's now something new. So the chemical makeup has therefore changed. So now let's look at chemical changes. So what would chemical changes be then? Well, they're going to be chemical reactions that alter the chemical makeup. So we have 3 examples here that we're going to go through. First example, this would be combustion, right? So we see flames, flammability, right? Burning. So anytime you see flammability, burning, combustion, that's going to be a chemical change, because when fire is involved, you are changing the chemical makeup of the substance itself. The next example, this is showing a car rusting. So rusting is also a chemical change. Why? Because when you have a car rust, it is no longer metal. That metal is turning into iron oxide. You have an actual reaction happening. You can get holes in your car in the metal due to rusting because the chemical makeup of the car is being altered, making it a chemical change. The last example, we see an apple molding. So any type of mold is going to be a chemical change, right? You probably wouldn't eat that apple when it's molding. And why wouldn't you eat it? Because it's no longer an apple. The moldy parts are not apple. They are now a new substance because a chemical change has occurred. So let's do some practice problem with chemical and physical changes. So here are some examples. Let's identify them as either a physical or a chemical change. So starting with the first one, a metal sign rusting. Keyword here is rusting. As we saw on the previous slide, rusting is going to be a chemical change because you are changing the chemical makeup of the substance. It is no longer the same substance. It's no longer metal. It is now iron oxide. Water freezing is the next example. So here, the keyword is freezing. So in this case, we're changing the state of the matter, not the identity. So it's still water, it's just it went from a liquid to a solid. So since the chemical makeup didn't change and we're still using water, it is a physical change. So put a big P there for physical. Next, number 3, crushing a cube of sugar. So crushing a cube of sugar, imagine coming along with your fist and just smashing a cube of sugar. Is that chemical or is that physical? It's going to be a physical change because it's still a cube of, it's still sugar. It's just no longer in a cube. It's now spread out. So you change the shape of it, but you didn't change the chemical makeup. Number 4, digesting a steak. So keyword here is digesting. So once you eat a steak and it goes into your stomach, is it still a piece of steak or does it change into something different? It's going to change into something different. The acid in your stomach is going to change it. It's no longer going to be steak, so it's a chemical change. Now let's go back to that metal sign again. So instead of that metal sign rusting for number 5, it is getting heated up in that hot Georgia sun. So is that going to be chemical or physical? So getting hot is a temperature change. And if you remember, temperature is a physical property. So something changing temperature is going to be a physical change. Last but not least, a gas can exploding. Keyword exploding, right? Flammability, explosion, combustion. It's going to change the makeup. It's no longer going to be gas once that fire's done. It's going to be a new substance, so it is a chemical change. Kind of a weird C, but all right. Now, a good question to ask yourself, you can see this little asterisk down at the bottom, when you're trying to figure out if the example is chemical or physical change, is can it be reversed? If it can be reversed, it's going to be a physical change. If it cannot be reversed, it's going to be a chemical change. So for instance, let's go through these examples quickly. Looking at rusting. Rusting cannot be reversed. Once something is rusted, you have to replace that piece. So that's why it's chemical. Water freezing. Can freezing be reversed? Yes, you heat it back up. It's going to change back from that solid ice cube into liquid water. So since it can be reversed, it is physical. Crushing a cube of sugar. This one's a little harder to see, right? Because you see a pile of sugar, you're like, how do I reverse that? Yeah, it's hard to reverse it and get it into a cube, but it is possible. So it can be reversed, it's physical. Looking at digesting a steak. Can you reverse that? No, once it's digested, it's got to keep moving through your system. There's no way to get that steak back. Not reversible, so chemical. The sign getting hot, right? This is similar to number 2, temperature change. If it gets hot, it can cool down again. So it's physical. And last one, the gas can exploding. Yeah, that gas is gone. You're not getting it back. It cannot be reversed, so it's chemical. So now we're going to go through another example, a situation. So in this situation, imagine you are working in a lab and you're studying a metal's characteristics and properties. Chemical properties as well as physical. You are given a roll of metal ribbon shown in A. You unroll a 30-centimeter strip to cut the metal into smaller fragments. So you cut it up and that's how you get B here. Now you isolate one of those small fragments that you just cut up and you drop it into some water. When you do that, it bursts into flame in picture C here. So now the questions are asking, question 1, what are the physical and chemical properties present in the metal? And then number 2, what physical changes or chemical changes are there? Now, physical properties, endless amount. right? So when you're looking at physical, that's anything that you can observe without changing the chemical makeup of the substance. So for physical properties, you can look at the color of it, you can look at the luster, you can feel the texture, the size, because they talk about unrolling a 30-centimeter strip. So length is a physical property of that as well. So and there's many more that I haven't mentioned, lots of physical properties. Now for chemical properties, those are a little bit more difficult, right? Those are things that can alter the makeup. So in this particular one, I guess flammability is the only one that I see because of the bursting into flames, but there could be more. So looking at number 2, these are the changes. So for the physical changes that are happening in this exact situation, I would say one of the changes is you're cutting it into smaller sizes. So the length is changing for a physical property. For the chemical change, I would say that would be flammability or combustion, it bursting into flames when you add the water. So let's look. You can see my little answers here. So for physical properties, they have shiny, lustrous, pliable, so meaning it can be bendable easily, weak enough to cut, that's a good one. The color being silver, it being metallic. Ooh, emitting a yellow-white flame. So now they're talking about the physical properties of the flame itself. So that's a good one. And then as we can see for chemical properties, the only one present in the situation itself is the flammable or the flammability of it. Next, we're going to look at pure substances versus mixture. First, looking at pure substances. So pure substances can be separated into two categories, elements and compounds. So elements are going to be when only one type of atom is present. So if you look at the periodic table is made up of elements. So oxygen, for instance, is an element on the periodic table. Oxygen is only going to be made up of oxygen atoms. Now, looking at compounds. Compounds are when two or more types of atoms are present. So this would be like citric acid, where citric acid has carbon and hydrogen in it. A more common compound that you know of is water. So water is going to have hydrogen and oxygen in it, meaning it is made up of two different elements, hydrogen and oxygen. Now looking at mixtures. Mixtures are separated into two categories as well. We have heterogeneous and homogeneous. So what is the difference between a heterogeneous mixture and a homogeneous mixture? Well, heterogeneous mixtures are going to be easily separated. What do I mean by that? So the example that I like to use for heterogeneous mixtures is vegetable soup. So with vegetable soup, you have the noodles, the letters, right? You also might have pieces of carrot. You also might have broth. So this is a heterogeneous mixture with several different substances in it. And those substances are easily distinguishable because you can look at them and tell, oh, that's a letter, that's a piece of carrot, there's some broth. They're also easily separated. You can take your spoon and pick out a letter or a carrot or just some broth if you wanted. Now, homogeneous mixtures then are going to be different. They're going to be undistinguishable, very difficult to separate. So an example that I like to use for homogeneous is salt water. So in salt water, you have salt present, sodium chloride, and you also have water present. So there's two different compounds, pure substances, salt and water, being mixed together to form a mixture, a homogeneous mixture. Now, when you have salt water mixed together, what happens is the salt dissolves in the water, right? So when you look at it, there's no way to easily separate the salt from the water unless you were going to evaporate all of the water off. So making it difficult to separate. So that's the difference between heterogeneous and homogeneous. So I like to think of heterogeneous as non-uniform and homogeneous as uniform mixtures. Another way to tell them apart as well is homogeneous mixtures are usually see-through. So what I mean by that is they might have color to them, but you can usually see through. They're transparent. You can see through the substance. Whereas heterogeneous mixtures, they're going to have some sort of solid or sediment floating around in the mixture. So let's summarize. Everything around us is made up of matter, because as we defined on the very first slide, matter is anything that has mass and occupies space. So that's everything around us, including the air that we breathe. So matter is separated into two categories, pure substances and mixtures. Now the pure substances, as we saw earlier, are further separated into elements and compounds. So elements being those elements on the periodic table, there is no simpler form by chemical or physical means. And then compounds are going to be two or more elements combined in a reproducible way. Now on the other side here we have the mixtures, and remember mixtures are two or more substances together. So maybe two or more compounds together or two or more elements together. So mixtures were separated into homogeneous and heterogeneous. So remember, homogeneous mixtures are uniform throughout. So if I took a sample of a homogeneous mixture or two samples of homogeneous mixture and analyzed them, both samples would be exactly the same. Now looking at a heterogeneous mixture, heterogeneous was not uniform, right? So if I took two samples of a heterogeneous mixture, so think back to that vegetable soup, if I took 2 spoonfuls of the vegetable soup, those 2 spoonfuls are not going to be exactly the same, right? One might have more broth, the other might have more vegetables or more noodles on it. So since we are talking about mixtures, we need to also look at how to separate mixtures. So here are some common separation methods, and we'll focus on the separation methods mostly in lab, but we do want to introduce them in lecture. So the first separation method, which you'll see used in lab often, is filtration. So filtration is when you are separating a heterogeneous mixture, meaning easily separated. So this would be, say you had a sand and water mixture. So you could separate that by filtration, where you pour the mixture through a funnel with a filter in it, and the liquid part of the heterogeneous mixture will go through the filter paper into the Erlenmeyer flask, and the solid part of the heterogeneous mixture will then be stuck in the filter paper. Centrifugation is another separation method, and we will not use this one in this lab, but how centrifugation works is it separates liquids by their density. So this could be used for homogeneous mixtures as well, ones that are more difficult to separate. So you balance out the test tubes in the centrifuge, turn it on, it spins around really fast, making the more dense materials go towards the bottom of the test tube, and the less dense materials will go towards the top of the test tube. Decantation. You will hear this word in lab quite often, decant the mixture. Okay, so this isn't a very accurate way to separate, especially if you have things floating on the liquid here. But we do use it in lab because it is a fast and simple method to use. So to decant, what you do is you let this solid part, and this is only done for heterogeneous mixtures, mixtures that are easy to separate. What you do is you let the solid settle to the bottom, and the liquid then will separate from that solid. Then you carefully pour, and that's what decant means, carefully pour the liquid portion off into a new beaker, leaving the solid behind in the old beaker. Now the last separation method we're going to look at is magnetic separation, and that is when you have magnetic particles in solution and you can use a magnet to get them to one side so you can pour the liquid off. Next, let's look at an example situation. So in this example, you are preparing a tea with tap water and sugar, but the bag of tea leaves breaks. Oh no. And then inside the cup, and you have now a tea with tea leaves floating all around inside of it. So what are the questions with this situation? The first question is, how would you classify the substances in bold? So what do they mean by how would you classify? Is it a pure substance? And if so, is it an element or a compound? Is it a mixture? And if so, is it homogeneous or is it heterogeneous? So let's look. First, let's start with the tea. So the tea itself, so we're looking at this picture here. So if you had the tea without the tea breaking or anything like that, would that be a pure substance or a mixture? Well, it's obviously going to be a mixture because you have water in there plus whatever came out of the tea leaves, right? So since it's a mixture, is it homogeneous then, or is it heterogeneous? Well, if the tea bag didn't break, looking at this picture, I can see through the tea. There are no solid particles in it. It is see-through, so that would be a homogeneous mixture. One sip of tea would have the same concentration and taste as the second sip of tea, so homogeneous. Next, let's look at tap water. Now, tap water coming out of the faucet. Is this going to be a pure substance or a mixture? Well, a lot of people want to say pure because water, but tap water, specifically the word tap in front, means that it is actually a mixture, because when you get tap water out of the faucet, it's not 100% H2O. It has other stuff in it, right? There might be some fluoride in it. There might be some other impurities in it. So it is indeed a mixture. However, it should be a homogeneous mixture because you should be able to see through it. Now, if you happen to have tap water that has things floating in it, then it would be heterogeneous. So that is dependent upon your specific tap water, but usually tap water is homogeneous. Okay, next, sugar is the next bold one. So looking at sugar, would this be a pure substance or would this be a mixture? So it's a little tricky. Sugar is actually a pure substance. Now, is it an element then or a compound? Well, if you look at the periodic table, sugar is not an element on the periodic table, so then it must be a compound. And it is. It's actually a compound made up of carbon and hydrogen. So sugar, pure substance, compound. Next, let's look at the tea leaves. So if you look at the tea leaves in a tea bag, right, the tea leaves are a solid. You're not going to be able to see through them. If you take one sample of the tea leaves versus another, it's probably going to be different because there's several different things in there. So it's going to be a heterogeneous mixture. So tea leaves, heterogeneous mixture. Now the last one in bold is the tea and tea leaf mixture. So this is this guy right here. Now that is obviously a mixture. They even gave that to you here in bold, saying it's a mixture. So is it heterogeneous or homogeneous? It's going to be heterogeneous because there's particles floating in there that you can separate out. So all of the answers are given there as well. To separate the mixture of this last one, you would use filtration would be the best way, mainly because of these floaty guys on top. If all of the tea leaves sank to the bottom, you could use decantation as well. Let's look at some more practice. So given these examples, identify each as a pure substance, a homogeneous, or a heterogeneous mixture. So the first one, hydrogen gas. Is that going to be a pure substance, a homogeneous mixture, or heterogeneous? Hydrogen is an element on the periodic table, so that is going to be a pure substance. Okay, next, looking at a soft drink. So think Coca-Cola, Mountain Dew, Pepsi, whatever your favorite soft drink is. Well, that's not going to be a pure substance, so is it going to be homogeneous or heterogeneous? Well, if you look at a soda, can you see through it? Other than the bubbles, right, the carbonation affecting your sight, yes, you can see through it. So this is actually going to be a homogeneous mixture, and that is because the carbon dioxide, the bubbles, the carbon dioxide, is dissolved in the liquid. So soft drink would be homogeneous. Next, saline solution. So what is a saline solution? It's really just salt water. It's salt dissolved in water. So we know then it's going to be a mixture. Anytime you see the word solution, it's not a pure substance. There's a hint right there. So salt dissolved in water, that is going to be homogeneous, because if I took one sample of a saline solution versus another, they're going to have the same concentration. Next, gelatin with cut up strawberries in it. So this is definitely a mixture, not pure. Would it be homogeneous or heterogeneous? Well, if it was gelatin just by itself, so just Jell-O, it would be homogeneous because you could see through it. One sample would be the same as the next. If you think about how you make Jell-O, right? You dissolve the solid Jell-O in water until it's uniform throughout. So it would be homogeneous if it was just the Jell-O by itself. But since it has the cut up strawberries in it, now we have made it heterogeneous because there are solid particles in it that we can remove. It is now not uniform. So gelatin with cut up strawberries, heterogeneous. Last but not least, pure sugar. Hint here is the pure. Remember we looked at sugar on the previous slide and we said that it was a compound. So pure sugar would then be a pure substance. The second part of chapter 2, we will be covering basic measurement prefixes, exponential notation. We'll learn how to use dimensional analysis, which is conversions. Also talk about temperature conversions and the Fahrenheit, Celsius, and Kelvin scales. And then, of course, look at density as well. Here are the vocabulary terms that we'll be going over in the second part of this chapter, and also the equations that you can see here. As for the equations, most of them are temperature equations to convert between Fahrenheit, Celsius, and Kelvin. I do want to point out that those equations are not supplied for you on the exam, so you will need to memorize those equations. Also, we have the density equation here as well, which is mass divided by volume. You'll need to memorize that one as well. We'll be doing several examples, so you'll get lots of practice, and that will hopefully help with the memorization aspect. So next we're going to look at scientific notation, often referred to as exponential notation. So scientific notation is when a number is represented as a power of 10. This is often used with really, really large numbers or very, very small numbers. It's an easier way to represent large and small numbers because then you don't have to write all of those zeros, right? So it's shortening the number itself by representing it in scientific notation. So for the examples shown here, this is just showing how positive exponents are different than negative exponents. So when I use the word exponent, I'm talking about the number that the power is raised to. So 10 to the positive 1, or 10 to the 0, or 10 to the negative 1. Those are all going to be the exponents. So you'll notice in the first example, where we have 1 times 10 to the positive 1, that is going to equal to 10. So what this is showing is when you have a positive exponent, the number is actually getting larger. So the number went from 1 to 10 when you applied the exponent to it. It got bigger. Now in this middle example, we have 10 to the 0 power. So whenever you see 10 to the 0 power, that's kind of tricking you. Sort of, it's basically telling you the number stays the same. So whatever number is before the multiplication sign, when you have it 10 to the 0, that number is going to remain the same. So in this case, there's a 1 in front of the multiplication sign, so the number just stays as a 1. Now in this last example, we have a negative exponent. So 1 times 10 to the negative 1. So in this case, it's showing that when you have negative exponents, the resulting number in normal notation is going to be less than 1. So in summary, the example below, 0.081. So since 0.081 is a number that's less than 1, we know it's going to have a negative exponent. Any numbers that are larger than 1 are going to have a positive exponent. So in the case of 1 million is a number much, much greater than 1. So if we were to represent that number in scientific notation, it would have a positive exponent. So that's the takeaway from this slide. Positive exponents, numbers larger than 1. Negative exponents, numbers less than 1. So you're going to need to know how to take normal numbers and represent them in scientific notation, and then also to do the reverse, to take scientific notation numbers and get them into normal notation form. So we're first going to look at how to take a normal notation number, which are the numbers you're used to seeing, and how to represent them in scientific notation. So the first rule for putting a normal notation number into scientific notation is that you want one non-zero number to the left of the decimal. So in the example below of 29 million, when you are taking that number and representing it in scientific notation, the first step is to put a decimal between the 2 and the 9. Why there? Because the first rule says you want one non-zero number to the left of the decimal. And if I put the decimal between the 2 and the 9, I will have succeeded in having one non-zero number to the left of it. Next, figure out what the exponent is. So how do you know what the exponent is going to be? Well, the exponent is going to be however many times you had to move that decimal in order to get it to where it now is. So in the case of the 29 million, we said we wanted the decimal between the 2 and the 9. So imagine that you have to start at the end of the number, so after that very last 0. Now to get that decimal point between the 2 and the 9, you have to move it 1, 2, 3, 4, 5, 6, 7 times to get it between that 2 and 9, meaning your exponent then is going to be 7. Third step is to tell, is the exponent going to be positive or is it going to be negative? And that's what we saw in the previous slide. In this case, the exponent is going to be positive because the original number was greater than 1. Remember, large numbers, positive exponent. Small numbers, numbers less than 1, negative exponent. Okay, if you have a hard time remembering that, you can also just remember the direction that you go. For instance, to get the decimal between the 2 and the 9, we had to move to the left. If you move to the left, positive exponent. If you move to the right, negative exponent. Now, last but not least, you want to make sure that you're only keeping significant figures. So you might want to, before you start moving any decimal points around, count how many significant figures there are in that original normal notation number, because that's how many you're going to want in the scientific notation number. So in the case of 29 million, only the 2 and the 9 were significant. All the other zeros were not significant because in the original number there was no decimal point. So trailing zeros do not count if there is no decimal point present. Looking at the other example here of 0.003303. So in this case, same rules apply. You want to put the decimal point between the 2 3's because that will make it so there's one non-zero number to the left of the decimal. To get the exponent, you count how many times you had to move that decimal point to get it between the two threes, and in this case you have to move it 4 times. Now the reason it is a -4 for the exponent instead of positive is because the original number was less than 1, so that gives it a negative exponent. Notice only the significant figures are kept. Those first zeros don't count because we don't start counting till we get to our first non-zero number when we're counting significant figures. So we didn't start counting till we got to that first 3. So 3, 3, 0, 3, those are the 4 significant figures. So we want to keep all 4 of those in the scientific notation form. Now that we are looking at scientific notation, let's do a quick review on significant figures. So whenever you are representing numbers in scientific notation, before you start moving the decimal points around and figuring out what the exponents are going to be, you want to take the original number and count how many sig figs are in the original number. However many significant figures are in the original number, that's how many sig figs you want represented in the scientific notation form as well. So let's look at this first example. Remember when counting significant figures that you always start counting at your first non-zero number, and you always go from left to right just like reading a book. So in this first example of 91,010, we start counting at the 9 because that is the first non-zero number that we encounter. The one next to it then also counts as a significant figure. Now this 0 here between the two ones, that is going to count because remember sometimes zeros count and sometimes they don't. In this case, this 0 counts because it's between two non-zero numbers. So anytime you have a 0 between two non-zero numbers, it does count as a significant figure. Moving on to the next number, 1, that is a non-zero number, so that counts as well. So the only number in here that's not significant is this trailing 0. Remember the rule, trailing zeros or zeros at the end of the number only count if there's a decimal point and we've already started counting. So that's why this 0 does not count, because there is no decimal point in the number. So we have a total of 4 significant figures in that number. So when we represent that number in scientific notation, we make sure to only represent those 4 digits, leaving off that trailing 0. Also notice that the decimal point was put between the 9 and the 1 because you always want one non-zero number to the left of the decimal when you're representing scientific notation. And then we have a +4 for the exponent because if we start moving the decimal place, so we can put a decimal at the end of the number, and we have to move that decimal 4 times to get it between the 9 and the 1. Since the original number was greater than 1, it is a positive exponent. Let's look at the next example. So in this example, when we're counting significant figures, we don't start counting till we get to this first 1. It doesn't matter that there's a decimal point here because these first zeros are not going to count because they can't. We can't start counting until we get to our first non-zero number. And when we go from left to right, the first non-zero number is this number 1. So that number 1 counts as our first significant figure. The number 2 would be the second. And then this trailing 0 in this case does count. It is significant. Why? Because there's a decimal place and we started counting at the 1. So there's a total of 3 significant figures in this number. When we represent this number in scientific notation, we want to make sure that the new decimal place is between the 1 and the 2. To get the decimal between the 1 and the 2, we have to move the decimal place 1, 2, 3 times to the left, and we get a negative exponent because the original number was less than 1. Now let's look at some examples. So for the first one, we have 0.0180. The first step when taking a normal notation number and changing it into scientific notation is to count the significant figures. It's important to do that first before you start moving decimal points around and things get a little messy. So when we're counting the significant figures for this first number, we don't start counting till we get to the 1 because that's our first non-zero number. So the 1 counts, the 8 counts, and then the 0 after the 8 will also count as a significant figure. Why? Because there's a decimal point in the number and we already started counting at the 1. So there's a total of 3 significant figures in this number. Next, we want to place a decimal, the new decimal place, so that there is one non-zero number to the left of the decimal. So our new decimal will go between the 1 and the 8. Now, to figure out the exponent, that is how many times you move the original decimal point to where the new decimal point is going to be. So in this case, I'm going to start at the original decimal point between the two zeros, and it looks like I have to move it 2 times to the right to get it between the 1 and the 8. So that means that my exponent value is going to be 2. Not only that, but it's going to be -2 because the original number was less than 1, giving us a negative exponent. So our answer in scientific notation is 1.80, giving us 3 significant figures before that multiplication sign, times 10 to the -2. Let's look at the next one. Counting significant figures, we start counting at the 6, so the 6, the 7, and the 3 all count. Do those trailing zeros count? In this case, they do not. Why? Because there is no decimal point in the number. So the trailing zeros will not count. Now, where do we want our new decimal place when representing this number in scientific notation? We want it between the 6 and the 7. So to figure out the value of the exponent, we now need to figure out how many times we have to move the original decimal point to get it between the 6 and the 7. Now I already said that this number doesn't have a decimal point in it, so when you're figuring out where to start, you just start at the end of the number. So I'm going to start at this last 0, and it looks like I have to move the decimal 1, 2, 3, 4, 5 times to get it between the 6 and the 7. So that is going to give me a positive exponent of 5 since the original number was much greater than 1. So the final answer being 6.73 times 10 to the 5th. Looking at the next one, in this one, the 1 and the 5 count, but now looking at these two zeros, notice there is a decimal at the end of the numbers. So since there's a decimal point in the number, these two zeros count. That decimal point's there telling you those zeros matter, don't forget about them. So we have a total of 4 significant figures in this number. Now for our new decimal place, when we represent it in scientific notation, we want that between the 1 and the 5. So to figure out the exponent, we have to move the decimal point 1, 2, 3 times to get it between the 1 and the 5. Since the original number was greater than 1, it's going to be a positive exponent of 3. So our answer in scientific notation is 1.500, can't forget those zeros, times 10 to the positive 3. Now let's look at numbers represented in scientific notation, and let's move them now to normal notation. So to go from scientific to normal notation, we pay attention mostly to the exponent. So in this first one, the exponent is 7. Not only that, but it's a positive 7. So since it's a positive 7, what that tells us is the original number was big. It was much, much bigger than 1. So when we move this decimal place, we know we need to move it 7 times, but since it's positive 7, that means we want to move the decimal point to the right to make the number bigger. So moving it 1 time, I get it on the other side of the 9, and then I'm going to move it 1, 2, 3, 4, 5, 6 more times. Now when I move it 6 more times, you'll notice there's empty spaces. So what's going to go in each of those empty spaces are zeros. Now it's kind of hard to write with this platform, so I'm not going to write the zeros here. I'm just going to show you what the answer would look like. So you'll notice the normal notation number is 29 million, and notice there are 6 zeros added to it because of those 6 empty spaces that I had when I moved the decimal point. Also notice that since there were 2 significant figures in the original number, we only have 2 significant figures in the normal notation number. These trailing zeros don't count because we didn't put a decimal point at the end, so that's very important. All right, let's look at the next one. Now for the next one, I'm going to count the significant figures first. I kind of skipped that on the last step. So looking at the numbers before the multiplication sign, it looks like we have 1, 2, 3, 4 significant figures. So we want to make sure to only have 4 significant figures in our normal notation answer as well. Now to figure out what this number looks like in normal notation, we focus on the exponent. So the exponent is 4, telling me I'm going to have to move that decimal point 4 times. Now in this case, the exponent is negative. So I'm going to move the decimal point, to the left. I'm going to make the number smaller. That negative exponent tells me the original number was less than 1, so that's why I'm moving the decimal point to the left. So I'm going to move it 1, 2, 3, 4 times to the left. So in these empty spots are going to go zeros. So looking at the final answer would be 0.0003303. Now notice there is still 4 significant figures because the numbers before that first 3, or the zeros before that first 3, don't count because we can't start counting till we get to our first non-zero number. So the 3, the 3, the 0, and the 3 are those 4 significant figures. So scientific notation, why is it useful in the science field? Other than a quick way or a shorthand way to represent really, really large numbers and really, really small numbers, which we've already discussed, it also works really well with the metric system. And if you remember, the metric system is what the SI units that are used in sciences and mathematics are based upon. So since we most often use the metric system in chemistry, it pairs really well with scientific notation, because as you can see from this table shown here, the first column we have the prefixes of the metric system. The ones highlighted in yellow are the ones that we are most often going to use in this course and that are most often used in most sciences. Next to the prefixes are their abbreviations. The one thing I want to point out about the abbreviations is if you look at the mega, it has a capital M for its abbreviation. And then milli, further down, has a lowercase m for its abbreviation. I like to point that out because you need to pay attention if it's a capital M or a lowercase m, because that is a big difference, as you can see. Now looking in the next column are the meanings. So for mega, the meaning is 10 to the 6th, or million. So notice the meaning is in scientific notation, because in order to convert between metric units, all you have to do is move the decimal point, because converting between mega and kilo, for instance, you're going to be moving the decimal point 3 times. So representing it in scientific notation is helpful because we're changing it by units of 10, and that's what scientific notation does. So let's look at mega once again. So what does mega mean? We said it means million. That's the meaning of it. So if we were talking, for instance, about a megameter, so we're talking about unit of length, meter. 1 megameter is going to equal 1 times 10 to the 6th meters. That's given in the example as you go across that row. 1 megameter is equal to 1 times 10 to the 6th meters. What that means is, if we put that in normal notation instead of representing it in scientific as 1 times 10 to the 6th, this tells us that 1 megameter is actually equal to 1 million meters. Much like if we go down to kilo, 1 kilometer is equal to 1 times 10 to the 3rd meters, or if we put that in normal notation, it would be equal to 1,000 meters. So 1 kilometer is equal to 1,000 meters. Now let's do one that has a negative exponent. So let's go down to centimeter. So centi, so if we're talking about length again, meters, 1 centimeter is equal to 1 times 10 to the negative 2 meters. If we put that in normal notation, it is 1/100th. So 1 centimeter would be equal to 1/100th of a meter. So that'd be a fraction or a decimal point in that case. So scientific notation really helps us apply the metric system and do metric to metric conversions, which we're going to look at when we talk about dimensional analysis. And I'll show you a shortcut way when we're doing metric to metric conversions as well in class. You'll notice in the example that they have on this slide, the normal notation number is a number less than 1. So when we write it in scientific notation, you can see it has a negative exponent. Also notice significant figures were kept since there were only 2 significant figures in the original number, and that the decimal was placed so that there was only 1 non-zero number to the left of the decimal. Next, we're going to look at accuracy versus precision. So you'll need to know the definition of accuracy and precision and be able to apply it to situations. So let's define accuracy first. So accuracy is the agreement between the true value and the measure value. So I like to look at this in the case of a dartboard. So accuracy would be how close are you to the bullseye, because the bullseye is the true value. So if you are hitting the bullseye every time, you are extremely accurate. If you are nowhere near the bullseye, you are not accurate at all. Then let's look at precision. So precision is measurement of the agreement of multiple measurements. So looking at the dartboard once again, you can be precise even if you're not hitting the bullseye. For instance, if you keep hitting the same spot over and over again, but that same spot is in the upper right-hand corner, far away from the bullseye, you are still being precise even though you are not being accurate. So if you keep getting the same results, you're precise. If you get a correct result or really close to the correct result, you are accurate. So there are cases where you will be neither accurate nor precise. So you'll be getting a wide variety of measurements, non-precise measurements, and you're nowhere near the true value. Then there'll be other times where you are both accurate and precise. So this would be where you're hitting the bullseye every time on multiple occasions, making it precise. So here's a situation that we will go through in class, and I will cover a little bit here in case you miss lecture. So in this situation, we're trying to determine the mass of an unknown solid added to a cup. So we have the mass of the cup, 37.65 grams. And then you add the solid and you measure it again. And this meaning you're measuring the cup with the solid in it. So when you measure the cup with the solid in it, it is now 67.2896. Now the first question asks, what is the mass of the solid from the first trial? So you have the mass of the cup by itself with nothing in it at 37.65. And you have the mass of the cup with the solid. So to figure out the mass of just the solid itself, you'll need to subtract those two as shown here. Now the second question is asking if the actual mass of the unknown was 30.12, which trial would be the most accurate? And was the experiment precise? So looking at this, notice I have a table off to the right here with all 4 trials in it from the question as well as their masses. So the first trial we solved by subtracting, so we have the mass of 29.64. The other 3 masses were given to us in the last sentence of the situation, saying we repeated the process 3 more times and got the following data: 31.78, 28.12, and 29.93. Now, if the actual or the true value was 30.12, which of those 4 trials is the most accurate? So remember, accuracy is how close to the true value. So to figure this out, you would look at all 4 masses and figure out which mass is closest to 30.12. So it is between trial 2 and trial 4, and it looks like trial 4 is going to be the winner. 29.93 is closest to 30.12. So trial 4 is the most accurate. Now, was the experiment precise? That's difficult to answer. We wouldn't be able to answer that unless they gave us a range of precision. So not able to answer that one. Next, we're going to look at temperature conversions, but first we need to talk about the temperature scale itself because it probably is new for most of you. So we usually use Fahrenheit here in the US to measure temperature. In most other countries, they use degrees Celsius. But what we're mainly going to use, or at least be able to convert to, is going to be Kelvin. So Kelvin is the absolute temperature scale. So what I mean by absolute temperature scale is that Kelvin cannot go below 0. We know that Fahrenheit can go below 0, as can Celsius, but since Kelvin's an absolute scale, 0 is the lowest possible temperature of all things. So when we use the term absolute 0, that is where all atoms cease to move and everything is completely frozen in time. Cannot get colder than absolute 0. Absolute 0 has not actually even been reached in labs, although we've gotten close to it. So what you can see from the diagram over here, the temperature differences between Fahrenheit, Celsius, and Kelvin. You can see for water boiling, water boils at 212 degrees Fahrenheit and 100 degrees Celsius. And it also has the corresponding Kelvin temperature of water boiling at 373. Now water freezing, 32 degrees Fahrenheit, 0 degrees Celsius. For Kelvin, water freezes at 273. Now off to the left here, we have the conversion equations to go between Celsius, Fahrenheit, and Kelvin. So the first equation is when you are given degrees Celsius and you need to convert to degrees Fahrenheit. So to do that, you take whatever degrees Celsius was given to you in the problem itself and you multiply that by 9/5. Then you add 32 to it, and that will give you the degrees Fahrenheit. The second equation is when you are given degrees Fahrenheit in the problem itself and it's asking you to convert it to degrees Celsius. So to do that, you would take the degrees Fahrenheit given to you and subtract 32 from it. Now you want to make sure to do that subtraction first, or to put that subtraction in parentheses in your calculator before you multiply it by 5/9. Because if you enter all of that into your calculator without the parentheses around the subtraction portion, it's going to do the multiplication part first and you'll get an inaccurate answer. The last one is going between degrees Celsius and Kelvin. So to do that, it's a simple addition. You take the degrees Celsius and add 273.15 to get it into Kelvin. Now you'll notice you can only go from Celsius to Kelvin. So if a problem gives you the temperature in Fahrenheit and wants you to go to Kelvin, you're going to have to go through 2 different steps. You're first going to have to go to Celsius and then go to Kelvin. Here's another slide with temperature conversions. These are the same equations, I just wrote them differently. So the equations on the previous slide that have the 9/5 and the 5/9 in it, that tends to confuse me because I don't know which way I need the fraction to be. So I rewrote the equations slightly different in case it might be easier for you to memorize this version of the equation. It still works the same and you're going to get the same answer. It's just a different version that's easier for me to understand. Pick whichever version's easiest for you to memorize. So in this case, going between Fahrenheit to Celsius, you take the degrees Fahrenheit and subtract 32 from it, making sure to do that subtraction first, and then you divide by 1.8. To go between Celsius and Fahrenheit, you take 1.8 times the degrees Celsius that given to you in the problem, and then add 32 to it. And then of course you have your Kelvin equations below, and I included the reverse going from Kelvin to Celsius, where you would have to subtract. Remember also that absolute zero is 0 Kelvin. That's where all atoms cease to move. That's going to be important to know, I'm sure, for either a homework or a test question. Let's look at some practice problems doing temperature conversions. So the first one is going from Celsius to Fahrenheit. So when going from Celsius to Fahrenheit, you want to choose the equation where degrees Fahrenheit is equal to. So in these first two, I'll use the 9/5 version of the equation. So using this equation, you'll want to take that 40.6 degrees Celsius and plug that in where the C is in the equation. So once you plug that in here, you'll multiply 40.6 times 9/5 and then add 32 to it. Once you do that, you'll get an answer of 105 degrees Fahrenheit. Now notice the significant figures remain the same as well. There's originally 3 significant figures in the original number, and there's also 3 in your final answer. Now, let's look at the next problem. The next problem is going from Fahrenheit to Celsius. So in this case, you want to choose the equation where degrees Celsius is equal to. So here you want to take the 77 given to you in the question itself and plug that in where this degree Fahrenheit is before the subtraction sign. So if you put 77 in right here, you want to take 77 and subtract it from 32. Notice there's parentheses around this portion because you need to do the subtraction part first in your calculator before doing the multiplication. Otherwise, you'll get an incorrect answer because your calculator will automatically do the multiplication portion first. So 77 minus 32, and then multiplying that by 5/9 to get 25 degrees Celsius. Make sure to enter these on your calculator and make sure that you're getting the same answers and you're inputting it correctly. Most common mistake is just not being able to use the calculator appropriately. So once again, notice 2 significant figures in the original number and also 2 significant figures in your final answer. Let's look at one more problem. Now in this problem, we are going from Fahrenheit to Kelvin. So remember when we were looking at the equations themselves, you cannot go directly from Fahrenheit to Kelvin. So this is going to be a 2-step process. So we're starting at Fahrenheit, we'll need to go to Celsius first, and then once we're in Celsius, we can use the equation to get to Kelvin. So notice we'll be using this first equation, degrees Celsius is equal to. Notice this time I'm using the version where we have the 1.8 instead of the 5/9. And then you'll use the Kelvin equation to continue the conversion. So using the first equation, notice we put that 87.2 degrees Fahrenheit in where the F is, subtracting 32 from that, and then dividing by 1.8 gives us 30.7 degrees. Remember, you need to do the subtraction first in your calculator or put parentheses around it so your calculator knows to do the subtraction first. Next, we're going to take this 30.7 degrees Celsius and plug it into the Kelvin equation. So we'll be taking 30.7 plus 273.15, and that will give us a final answer of 303.8. Now notice this is not the correct number of significant figures. So if I go to my original number in the question, there are 3 significant figures. So I want to make sure to only put 3 significant figures in my final answer. When you're doing your homework problems, if it gives you partial credit, but not all credit, it is often likely that you either forgot the units or you have the incorrect number of sig figs. So pay attention to that when you're doing your second attempt on your homework. So this would have only gotten partial credit if I gave that answer. I would have needed to write 304 Kelvin with the correct sig figs to get full credit. Volume and density. So we're going to be talking about density and doing some calculations with density, but in order to do that, we first need to define and look at volume. So for volume, you can see there are some different measurements of volume given on this slide. You can measure solids, liquids, and gases using volume. It's not the most common unit to measure solids. Usually for solids, we use length measurements. But when we use volume measurements for solid, you can see it's really just the length cubed. So in this example here, the solid is being measured in meters cubed. We can also measure solids in centimeters cubed or inches cubed. Any type of length measurement cubed will be a volume. Now liquids we most often measure using units of volume. So for liquids, we'll most often see them being measured in either liters or milliliters. Last but not least, gases. Gases can also be measured in units of volume. You can see also there's a conversion factor here under volume, showing that 1 centimeter cubed, which is a unit of volume, is equal to 1 milliliter. So they are interchangeable. 1 centimeter cubed is 1 milliliter. Now going over to density on the right-hand side of the slide. The equation for density is where you take the mass divided by the volume. So it has the most common units that we're going to see for density given here. Grams per milliliter, so grams being the mass, milliliter being the volume. We'll also often see it in grams per centimeter cubed. So when we're talking about a solid, it'll be measured in centimeter cubed instead of milliliters. But luckily, centimeters cubed is equal to milliliter, so those units are interchangeable. The nice thing about density is we can use it to convert between mass and volume, which we'll see in some of the example problems. When we do the example problems, we're going to use the density equation triangle as a shortcut to help us figure out how to rearrange the equation depending on what the question is asking us to solve for. Because it's not always going to be straightforward in asking us to solve for density. Sometimes it'll give us the density and volume and ask us to solve for the mass, and other times give us the mass and density and ask us to solve for the volume. So how do we use this density triangle? Well, first off, to remember the triangle, it's pretty straightforward. It's DMV. Think about going to the DMV and getting your license. Now, the horizontal line is going to be division, as you can see by these division symbols. And anytime you have a vertical line, such as between the D and the V, it's going to be multiplication. So how do you use this equation? Figure out what you're solving for, and then cover that quantity with your hand and perform the calculations indicated left over. For example, if you needed to solve for volume, you would cover up the V with your hand, and what's left over is mass and density. And from the triangle, that means you should take the mass given to you in the problem and divide by the density in order to solve. In this situation, there's a hot piece of metal with a density of 11.7 grams per mil being dropped into water, initially at 25 degrees Celsius. What happens when you drop the metal into that water is that the water level is going to rise. So there's going to be a new volume of water. It's going to rise because the water is being displaced by the metal that is being dropped into it. So we have a lot of things going on here. We have the temperature changing. Temperature is rising because the hot metal is going in the cold water and heating it up. And then we also have the water level rising because of the displacement due to the metal being dropped in it. So looking at the questions given, what is the final temperature of the water in Kelvin? Well, to figure out the final temperature of the water in Kelvin, you need to first take the initial temp, which is 25 degrees Celsius, and add how much the temperature rose after adding the metal in it. So 25 plus 3.45. That will give you 28.45, and that's degrees Celsius. So to convert that to Kelvin, you'll need to add 273.15 to it. Now the second question is asking what the mass of the metal is. This is going to be much more intensive to figure out because we first need to figure out the volume of the metal. So what they gave us was the density, and then what the initial volume of the water was and the ending volume of the water was. So from just that information, we have to figure out the mass of the metal itself. So here's all the information that they gave us. Roadmap to figure it out. So I already discussed how we go from Celsius to Kelvin. Now let's look at the second question. So for the second question, to figure out the volume of the metal itself, we need to figure out the displacement. So the water level rose to 22.7 milliliters. Initial volume was 20.1 milliliters. So if I subtract those two volumes, what I'll be left with is the volume of just the piece of metal itself. So now I have the volume of just the metal, and I also have the density of that metal. So if we're looking at that density triangle, to solve, I have the density and I have the volume, and what I'm solving for then is the mass. So in order to solve for the mass, we need to take the density and multiply it by the volume. And that's what we have shown here in this calculation. We have the density multiplied by the volume. And when we do density multiplied by volume, we get 30.42. But remember, we learned about significant figures for a reason, so you want to keep using significant figures all throughout the semester through all of the problems. So looking at the sig fig, since we're doing multiplication, we want to look at total significant figures. So the significant figures in 2.6, there is 2 significant figures in the volume. Excuse me. For the density, there is 3. So we want to make sure there's only 2 significant figures in our answer.